Okay, we are recording again the audio only. So homoscedastic means that, like I said just now, for the bivariate normal, for each value of 1, the other one is distributed normally. For each value of 1, the other one has a similar range. That's what homoscedastic means, a similar width, similar variability. So again, if I'm comparing a correlation between age and height, if you're 14, the possible heights is like this, and the width is that. If you're 75, your possible heights are like this, and the width is like that. So the widths are somewhat comparable. Variation is somewhat comparable. That's homoscedastability, skedasticity, skeska, whatever. All right. So what you can do to test the significance of a Pearson's row, much like we've done for the t-test and things like that, is you compute your R, your rho, and you compute a degrees of freedom. Very easy in this case. It's just your n minus 2. You look it up in the back of the book. Don't worry about this R to Z transformation. I just pulled that slide from the textbook manufacturer. All that means is when you look it up in the back of the book, they have converted the rho scores to Z scores. It'll give you a headache if you think about it too much. Trust me on it. Don't worry about it too much. Right. So, and then you compare it to the back of the book. So a couple other points around the Pearson's row before we move on to the real meat of today. First is that Pearson's row, as I mentioned, gives us information about direction and magnitude. So the magnitude is the closeness of the grouping. The direction is the slope. And we can use it to measure effect size. So effect size is the degree to which two variables relate to each other. It's relevant if you're looking at a randomized controlled trial, looking at whether or not this drug works better than a placebo drug. The difference between how much they respond in their population, that's the effect size. So when we publish studies looking at whether or not drugs work, we're looking at the sizes of the effects, the effect size. So correlations can be used for effect sizes, but more typically we use R squared as effect size. And we call that the coefficient of determination. And R squared is very useful because if you remember from your midterm, it tells us the percentage of variation in that relationship that is explained by the other variable. Okay? So if I'm correlating your age with your height, and it's, you get a pretty good number correlated there. If my R squared for that is, say, 90%, I say that 90% of height is explained by age. So the reason that you're taller than you is because you're older than him or her, whatever it might be. That's essentially what we're saying statistically. And we call that the correlation of determination. So we can compute confidence intervals around rows as well, around Pearson's row. I won't go into the computations in this class because they're not fun. But just be aware you can do it. It's not hard. Notice for this one, is 0 in between here? It goes from minus 0.02 to 0.5. Is there a 0 in between that range? Yes, there is. 0 falls in between 0.02 and 0.5. And we said 0 correlation means nothing's going on. So if 95% of the time I have a good shot at getting a 0, it means probably 95% of the time that there's nothing going on. So this particular example tells us that the correlation that we computed is probably 0, or at least can be 0. We can conclude from this that there's no correlation likely. And that's how you read confidence intervals pretty much all the time. Hope you remember that. So the things that affect Pearson's row are, I mentioned range already, so correlating your age to the number of rooms in your house, different ranges. That's going to reduce how much correlation you appear to have, and whether or not the groups are extreme. So if I'm only correlating the extremely tall people and extremely rich people, and I'm asking, is height correlated with age, or with wealth? Probably I'll find nothing there. Of course, that's a bad example because height is not correlated with wealth. Let's look at height and age again. So for the extremely young, height or extremely short, those two things aren't well correlated. And the same for the extremely tall or the extremely old. But everything in between you can get. And the reason for that is you lose expression of the fullness of the variable if you're only looking at extreme variables. Having outliers. Outliers suck. So if we've got, again, correlating age with height, If I've got a 100-year-old dwarf, or like the tallest man in the world who happens to be like 6, that's going to really confuse my results. So these outliers will really pull down the degree of my correlation. So we don't like outliers. And if we have instruments with low reliability, do you know what reliability means in science? It has a specific meaning in sciences. I mean, it's not like you have an unreliable friend. That means that you can't count on him to do stuff. That's not what it means in science. What does it mean?
It means how reliably you can reproduce the results.
Exactly. Reproducibility. That's exactly right. So the degree to which you get the same result as you do the test over and over again. So if I have a blood pressure cuff that is unreliable, and I take my blood pressure 8 times in the next 8 minutes, I'll get strongly different answers each time. That's an unreliable instrument. So if I've collected my data with instruments with low reliability, I'm going to get poor correlation, when in fact age is correlated with blood pressure. My instrument of poor reliability will mask that phenomenon. So all these factors are associated with artificial lowering of correlation, of Pearson's correlation. So Pearson's correlation, again, is a parametric test. Do you remember what a parametric test is? We defined it last time. No. A parametric test is one that uses a parameter or assumes the existence of a parameter that requires knowledge of the distribution of the index in a general population. Some things don't require parameters. Chi-square is one of them. So the chi-square test didn't involve looking at these theoretical distributions of stuff. So that's a non-parametric test. But we just said the Pearson's rho, we assume that in this super theoretical population of the universe, there is people perfectly correlated between age and height. And that's how the assumptions underlying these indexes arose. Okay. We also assume that it's applied to interval data. So age and height are both interval or ratio data. What if it's ordinal? Okay. Ordinal data is very different. Ordinal data, as I mentioned, is things like rankings. How well you do in this class compared to your colleagues is different from your mark. Ordinal data relies upon your performance relative to other people, rankings. Pearson's correlation coefficient is not meant for ordinal data. We'll have to do something different. So, we have to use a non-parametric approach, looking at ordinal data. And we're going to mention 2 non-parametric approaches today, Spearman's rho and Kendall's tau. Everything in statistics is named after somebody. Okay, and I always confuse Spearman's and Pearson's, and you're going to confuse them too, but I'm asking you, do not confuse them. So Pearson is the one that uses interval data, and Spearman's is the one that uses ordinal data, and they're quite different. Pearson's is also the one that's associated with straight lines. We're going to see it again with linear regression. Spearman's doesn't. Okay, so Spearman's rho looks at rankings of data. And Kendall's tau is more complicated. It also looks at rankings, but in a more complicated way. We are not going to compute Kendall's tau. We will compute Spearman's rho. Be aware that it exists, and be aware that both of them range from -1 to +1 the same way that Pearson's rho did. So let's compare Pearson's rho with Spearman's rho and Kendall's tau. That's not a T, that's a tau, Greek letter tau. So Pearson's rho, the first one we looked at, assumes interval or ratio rather data. That way range is important, outliers are important. Spearman's rho assumes ranks. So range has no influence. Doesn't matter. All it matters is that you got a higher mark than you. It doesn't matter how big that difference in marks was. Just that one was higher. And tau is a little more complicated. What tau looks at is whether or not the relationship direction changed. Like in one data set, you got higher than that guy. The next one, you got less than that guy. So it's a little more, it's the shifting back and forth that matters. Don't worry about it too much. We're not doing too much with Kendall's tau. Be aware that there are different ways of approaching this. And that's just a different way of doing it. So with Spearman's rho, the textbook uses this nomenclature. That's the Greek letter rho, and that's the subset, subtext S. I will use that. Same thing, doesn't matter. So we call this the Spearman rank correlation, or Spearman's rho, and it's like the Pearson's rho, but it's the Pearson's rho that's been applied to the rankings, not the pure data. So remember, Pearson used interval, we're going to use the rankings of that interval data. Right? We also call it a rank order coefficient. And Kendall's tau, if we can talk about this for a second, the thing to remember about Kendall's tau is we can do it with two ordinal variables, or we can do it with one ordinal and one interval. You can't really, or you shouldn't really do that with Spearman's rho. Spearman's rho should be two ranked variables. With Kendall's, it should be, you can do it with either two ranked or one ranked and one unranked. I'm going to step over my words a bit. It's going to confuse you a lot, and you're going to be a little bit more confused when we do their example, because the data will not appear to be ranked, but we're going to rank it. So when I ask you to do a ranked correlation coefficient, the data I give you may be interval or ratio. You're going to have to rank it to make it ordinal. That's why if you do it with SPSS, you can give it you can have SPSS correlate age with height, neither one of which are ordinal data, but you can ask it to do a Spearman's rho. What it will do, it will rank it and create an ordinal list out of that data and produce a correlation based on that. Now, many people think that Kendall's tau is actually better than Spearman's rho, but it's not as intuitive and it's harder to compute, so we tend not to use it. So that's the human element to all of this. The better test often doesn't get used because we don't understand it as well. It's not as much fun. So we're going to use Spearman's rho because it's easier to do. So Pearson's, if you remember Pearson's, again, I'm confusing them. So Pearson's is the first one we did. Pearson's is all about that linear relationship, that straight line, how much they group into a straight line. So for each rise in one thing, the other thing goes up the same amount. Rise equals run. So we get a kind of a straight line, ideally. Spearman's rho does not test for linearity. It tests for something called monotonicity. A monotonic relationship, not a linear relationship. What's a monotonic relationship? Well, a linear relationship is as one goes up, the other goes up the same amount regularly, so straight line. With monotonic, it doesn't matter how much it goes up, only that it goes up. Here's a graph of a monotonic relationship. It's going up, not at the same rate all the time. If you consider this to be speed and time of a car moving, the car is not accelerating at the same rate. It's accelerating at different paces, but it's still accelerating. It's not slowing down, not going backwards any time. This is not a monotonic relationship because at some point the car goes, change direction, and down again. So long as you're always going the same direction, it's monotonic. Monotonicity is more forgiving than linearity. Obviously, you can see that because I don't have to maintain the same acceleration. I can dick around a bit. So my computer is low on memory. Well, that's not good. Let me see if I can save this file before my computer crashes and we lose. Okay. Recording again. So these are linear relationships. Linear relationships are a kind of monotonic relationship because in a linear relationship, it's still going in the same direction all the time. It just happens to be kind of like how a square is a special parallelogram. A line is a special kind of monotonic relationship. So Spearman is robust to outliers. Robust means it doesn't change depending upon a changing situation. Right? So Pearson is not robust to outliers. Remember I said if you got an extremely young 8-foot tall person or an extremely old dwarf, you have extreme situations that's going to affect your correlation. That doesn't matter with Spearman's case because we don't care about the distance between variables. We just care about the rankings. So if you have a data set that has a lot of outlier, you can run Spearman's correlation on it and be confident that's not going to change things. Pearson is parametric. Spearman is not. So I'm the kind of dick. I ask you a question. Which of the following is not a parametric test? You know. Okay? And the difference is you don't need to know the original distributions to know what's going on. I mentioned with Pearson's, for each change in one, there's a distribution like that for the other. So 14-year-olds are distributed this way in height, 17-year-olds the same way. Doesn't matter with Spearman. It's non-parametric. Right, so this summarizes when you'll use what. So this is the test you'd use. This is how you write it down. That's whether it's parametric or non-parametric, and that's the kind of data you would use. Straightforward stuff. So Spearman's row is great. Why wouldn't you always use it? I've got one example of one reason up there, and that reason is it's not natural. It's hard to think about rankings. It's easier to think about numbers. Why would I correlate the rank of how well you did in class with the rank of how well someone else did in class? Why don't I just correlate your marks? So it's not natural. Are there other reasons you can think of why I would use Pearson's instead of Spearman? Remember, Pearson is the one with pure numbers, Spearman is the one with ranks. No? Can't think of any other reasons? All right, I'll let that one float for a while. I'm sure it'll keep you up at night thinking about it. All right, so here's some examples. Which of these requires rankings versus unranked correlational test? The first one, people's preferences in ice cream flavors with their calorie count. So calorie count is obviously how many calories are in the ice cream. Your preference would be, I like this one best, this one second best, this one third best, whatever it might be. Are those ranked, unranked, a mixture of the two? Are those variables ordinal? A ranked ice cream. So the first one is ranked. This is a ranked relationship. Second one, children's age and height. Are there rankings involved there? No. Age and height are pretty straightforward numbers. Those are unranked. Property tax with a number of rooms in a house. That's a difficult one. So tax is obviously the amount of money. That's a straightforward number. Amount of rooms in a house, you can look at it as a straightforward number, or you can look at it as an ordinal count as well. Most people probably see it as an ordinary number, right? So either one. And lastly, your favorite world cities with their average temperatures. So I like this city the best, that city the best. Anytime you have favorite anything, it's a ranked situation. So that's ranked. Notice that in both of these cases, one of the variables is ranked and the other one isn't. But because one of them is ranked, you can't do Pearson's. You must do either Kendall's tau or Spearman's. So this is the formula for Spearman's row, and you will be using this formula on the assignments you will do. And it's pretty straightforward. It's really easy. D is the difference between the differences. So we're going to do an example here. The example is there a positive significant correlation between the rankings of 6 kids on a reading test and how their teachers actually viewed their reading ability? This is a kind of real-life example because we often look at, is perception actually related to performance? So maybe I already have an idea of how good you guys, some of you are in statistics, because I've spoken to some of you already. Now let's see if my impressions of you are actually reflected in your performance on the exams. And there's all kinds of, when you take epidemiology, we'll talk a bit about this, all kinds of biases implicit in instructors' impressions of you that eventually reflect on your performance, have nothing to do with your actual intuitive abilities. Anyway, off on a tangent. So that's what we're ranking here. We're comparing whether or not kids' abilities are actually associated with their teachers' impressions of their abilities. So the reading scores are on an interval scale, 0 to 100, where 100 is great reader, 0 is crappy reader, and the teachers rank them from 1st to 6th. So number 1, best reader, 6 is the worst reader. So this is obviously ranked, and that's obviously interval. So because at least one of them is ranked, we're going to have to do a ranked correlation. I've already said we're going to do Spearman's correlation. So Spearman's correlation requires both of the variables to be ranked, so we're going to convert one of them to rankedness. So here is our data. Here are our kids. I've gone to great efforts to make it a multicultural list of names. Hope you appreciate that. And here are the reading scores and the rankings of the teachers. These are ranks. These are pure scores. If I were to just scatter plot those things, I'd get this. Is there a correlation there? Oh, you can see pretty well there isn't already. So we know we're going in not expecting a whole lot going on. Also, though, remember that, look at that range, 81 to 99. That's a very large range, actually, compared to this range here, 1 to 6. So the ranges aren't comparable. Already we know if we did the Pearson approach, we get a bias towards finding no correlation. That's how we're going to rank it. So first thing we do is we rank the interval variable to make it ordinal. So the guy who got the highest score, Bob, he gets scored first. The second highest score was Esmeralda. She gets number 2. And Frank, third highest, he gets number 3. And so forth until poor Wei, who scored the lowest, 81, gets number 6. And we're going to compare these two ranks. Now we have 2 ranked variables. That's what we do the math on. So the difference in ranks is this. It doesn't matter which one you subtract from which. Just be consistent, because we're going to square them. And we square them to take away the minus signs. So differences, square them, and add them all up. Right? Remember, our formula here is 6 times all of that divided by this little contortion here, subtracted from 1. And we get 0.03. So that's my correlation coefficient for Spearman's rho. Already, you see, that's pretty low. That's a pretty low correlation, not surprisingly. But what else can we do with that? Well, we have our degrees of freedom, n minus 2. In our example, there are 6 n's, so our degrees of freedom is 4. We can look it up in the back of the book if we want to, which is kind of pointless, to be honest. But we do it because the book says to do it, so we'll do it. So here is our null hypothesis, and alpha level 0.05. Look up in the back of the book, and we get, in the back of the book, alpha is 0.05. The critical rho is 0.886. So the book is bigger than our number, so do we reject the null or do we fail to reject the null? When the book's number is bigger than our number, we always fail to reject. Unsurprisingly, we knew that already. We knew there's no correlation. The null says there's no correlation. We failed to reject. There's no correlation. But we knew that already. So ours is less than the table's. We failed to reject. And, of course, we always answer the question. The question was, is children's ranking correlated with teachers' ranking? No, they are not. They are not simply correlated at all. If I simply ask, are they correlated? Well, it's greater than 0, so there is some correlation. But I ask, are they significantly correlated? The answer is no. At the alpha level 0.05, they are not. So, if I were to ask how much variation is there in teachers' ranking that is explained by the kids' reading, what would I do? How would I compute that? Yes?
I got a question about what is significant correlated.
Significant means, because we're talking about significance, we're talking about p-values. And we said that at the alpha of 0.05, this was not significant. So the p-value here is not less than 0.05. That's why we look stuff in the back of the book?
As long as it's greater, it's considered significant.
That's right. So we have to state our alpha, our cutoff. If we don't state it, the rule of thumb, as we say, is 0.05. Yes?
But you compare it to the row for 0.05, not 0.05 itself.
That's right. That's right, yes. Okay, cool. So if I'm looking, having said all that entire exercise of looking stuff in the back of the book for correlations, I think is pointless. Because in real life, we almost never look up p-values for correlation coefficients. They're kind of pointless to do so. What we usually do is this. We figure out how much variation in one is explained by the other. And do you remember how to do that? You square it. You just take the square. So 0.03 squared is not 0.09. I did the math wrong. It's 0.009. 009? Whatever it is. It's less than that. So there's not a whole lot of variation explained one or the other. So it's actually 0.9%. Okay. So SPSS, to do so, you choose the bivariate analysis, and you have to select Spearman's rho. It tells you which one to select. If you don't select it, it won't give it to you automatically. That's ranked correlation. Any questions about it? It's actually really, really easy. It's probably one of the easiest things to do in this class. Yeah? So most of the time we use Spearman's rho because it is forgiving towards outliers and things like that. But the answer as to why we tend to use Pearson's, in a lot of cases, even though Spearman's is better, in my opinion, is, as I mentioned, Pearson's reflects real numbers, so we're more comfortable. And the second reason is it leads us to linear regression. And we'll see this in a couple of weeks when we do linear regression, that R number just keeps on popping up, and it's really useful. That is all. Fast class. And I got to convert this audio now to YouTube because that is all. There it is. Oh, I got more stuff. Look at this. Oh, silly me. Rank of data, that's the important part. Here's another example. More examples? Oh, let's do an example. Let's do it. All right, let's go. I took an example from Wikipedia. I forgot about this. Is there a correlation between IQ and how many hours of TV you watch? So, are those ranked or unranked? Automatically, your IQ score and the hours you watch on TV. Well, the pure IQ score isn't, but you could rank it. The way it's expressed right now, it's not. But you could rank it. So these are not ranked numbers. These are just your IQ score. What we could do is say the highest IQ score is this guy here, 113. He gets number 1. The second highest rank is this guy here. He gets number 2. The third highest ranked is this guy here. He gets number 3. And so forth. Now, it gets really weird when you have ties, if they're the same. How do you rank it there? We'll cover that later. But here's a scatter plot between that relationship. It looks like something's going on, right? It looks like the more TV you watch, the less IQ you have. Interesting. I don't watch TV, just so you know. It's not true. I download. So here, these are ranked. They compute the difference. They square the differences and add them up. We get that. And plug it into a formula. 10 people. And you get... That's our correlation, 0.18. Not a very high number, but it's minus, which is telling. And we look up the significant. It's non-significant. So in fact, the rankings are not correlated at all. It looked like it was, but it wasn't. Curious. So it's okay. You can watch more TV. It's not lowering your IQ. Or at least if you have a low IQ, you're probably not watching any more or less TV than people with high IQs. Right? And this is the way it looks on SPSS. Remember that in SPSS, what they'll do is they'll create this matrix, and every time you're comparing something to itself, you're always going to get perfectly 1, but you want to compare it to something else. So TV compared to IQ is like minus 0.18. These are going to be symmetrical. So you can compare endless variables to endless variables, and it'll create a bigger and bigger matrix. That's how you read it. So... All right, let's talk about ties then. I got the slides up here. We have time, so talk about the ties. Obviously, I want to go home. I'm getting a massage in an hour, so I want to go home and get my massage. So, all right. So, what do you do if you have a tie? So here are people's English marks, and here are their math marks. Right. So these two guys have the same mark. How do you rank a tie? You give them halves. You rank them the same, but you give them a half. So it's not like they're both ranked number 6. Or both ranked number 7, or 1 6 or 1 7. You give them both 6.5. So if there's 4 ties, each would be 6.25 or something like that. Okay. So I want. I didn't upload that. So I'll upload the website right now, and try that assignment. And I think the answer is in the comment section of this slide. Let me see if it is. It is. Look at that. Good. Right on. For once, I did something right. Okay. Good. That's your homework. Okay. I mentioned the ties thing for your own education, but in this class, I will not give you any examples where there are ties. Because technically, if there are ties, the formula changes slightly into that, and you don't want to do that. But be aware that there is a mechanism for accounting for ties and ranking, and I've showed you part of that mechanism. But rest assured, in this class, I will not give you ties. All right? Whew. All right, thank you very much.